Well, welcome to lesson 2.5 in your book. This is on complex zeros and the fundamental theorem of algebra. And this lesson will be a continuation of what we've been talking about in chapter 2. We are going to be extending all of our properties to the complex number system. So a couple of things to recall. Multiplicity refers to the number of times that a factor occurs in a polynomial. We've been dealing with that and how that affects the graph of our polynomial. Another property that you should be aware of from our prerequisite chapter, if we have a factor a plus bi, then a minus bi is called its complex conjugate, and that will relate to our complex conjugate zeros theorem. And then the factor theorem says if we have a 0 c, then x minus c is the factor, and vice versa. If we have x minus c as a factor, c is called a zero, or a solution of the polynomial. So a couple of new theorems and properties for you. The fundamental theorem of algebra says basically whatever the degree of the polynomial is tells us how many complex zeros the polynomial has. And when we say complex zeros, that includes the real zeros that we've been finding, as well as the complex zeros that will be new in this lesson. And some of those zeros may be repeated. The complex conjugate zeros theorem says that if we have a plus bi as a zero, or a factor of a polynomial, then a minus bi is also a zero. Our odd degree polynomial property says that every polynomial that is an odd degree with real coefficients has at least one real zero. And factors of a polynomial with real coefficients, this is the one that we're going to focus on in this lesson. And basically it says that every polynomial that has real coefficients can be written as a product of linear factors and irreducible quadratic factors. And an irreducible quadratic factor is one where there are no real solutions. So as long as the solution is real, even if it is irrational, we will reduce it to a linear factor. And so we'll talk more about that later in this lesson. So let's start with an example. Suppose we have a polynomial function and these two zeros are given. What's the minimum degree of the polynomial? Well, these may be repeated zeros, but we're just going to assume that they are not. So x equals -2 would be one solution. That would give it degree 1. This one occurs in pairs. Whenever we have a complex solution, they have to occur in pairs. So 3 minus I will also be a 0. So the minimum degree of this thing is 3. To write the polynomial function in factored form, using linear factors, we already know how to write the real factor. That would be an x plus 2. But then this one we'll write as, and remember when we do that, what we're doing is we're taking x minus the opposite sign. So this one will be x minus 3 plus I, but then its complex conjugate pair will also be a factor. So here are your three factors. Okay, remember it's x minus and then the factor, so minus and minus 2, that's where we get the plus 2. And this is going to be very important for you to remember how to write these. It's always x minus the factor. Write the polynomial function as the product of linear and irreducible quadratic factors with real coefficients. So here's the part where we're going to be talking about this irreducible quadratic factors. And to do that, we can leave this first term alone. That's already written as a linear factor. But these two we need to use FOIL on and multiply. So I'm going to go ahead and do that. And when we use FOIL on this, our first terms give us x squared. This is our outer, this is our inner term, and then this is the product of our last term. So I just used FOIL on these last two terms. Then I need to distribute and get rid of all of these parentheses and then use FOIL on the last two terms. So here is that result. So we have x squared minus 3x plus xi. That's the distribution of the negative x here. Distributing negative x here, I get minus 3x minus xi. And then using FOIL here, we get 9 minus 3i plus 3i minus I squared. All right, lastly, combining like terms, and I've already written what drops out. We have a minus 3i plus xi minus xi. Remember, an I squared right here is equal to -1. So when we have minus a -1, this becomes a plus 1. Maybe I'll write that in here for you so that you know where that goes. So this term right here becomes a plus 1. and we're going to combine that with our plus 9 to get the plus 10. And then minus 3x is the minus 6x, and here's our x squared term. So now we have this written as a product of linear, here's a linear, and here is an irreducible quadratic factor right here. This one's irreducible because we get complex solutions. So part D says, write your polynomial function in standard form with those zeros that were given to begin with. Well, if we want to write this in standard form, now we need to distribute multiplying x plus 2 times this trinomial. So here we go. In the red, I've distributed x times the whole trinomial, and then 2 times the whole trinomial, and those are in green. And then combining like terms, we get x cubed minus 4x squared minus 2x plus 20. That is now in standard form, and it has those zeros. Example 2, given that function, list the possible rational zeros. Well, that comes from what we've talked about in the beginning of the chapter from lesson 2.4, where the p's come from the factors of 20, the q's are the factors of 3, and then all the possibilities are p over q, and so those are listed here. Use your graphing calculator to determine which of those possible zeros could be zeros, and then verify those. So I went ahead and did that for you, and I found that one of the zeros was negative 4. And here's the synthetic division showing that it is a factor. We get a 0 remainder. I also found that 1/3 was a factor. So using these 4 terms here, drop the 0 and do synthetic division again using 1/3, and I came up with this remaining 0 as a 0 remainder. And so then these are the terms that are left. Well, these 3 terms, we can write that as 3x squared minus 12x plus 15. But they share a common factor of 3, so if I factor that out, we're left with this. And now let's go ahead and write that with these 2 factors as well. And we're going to have x plus 4. I went ahead and wrote this as x minus 1/3, and you'll see why in a minute. When we distribute the x minus 1/3 times the 3, that's where we get the 3x minus 1. And so now I've written that down here, x plus 4, and then multiply these 2 together, we get the 3x minus 1. And then this one is x squared minus 4x plus 5. And so this one right here is an irreducible quadratic factor, and the way that you could check that, and you should check that, is to do the b squared minus 4ac thing from the quadratic formula on the trinomial, and you'll see that that is less than 0. You'll get a negative number, which means that your solutions to this quadratic will only be complex. So now it's an irreducible quadratic because we only have complex solutions. All right, our last slide here says, write this function as a product of linear and irreducible quadratic factors with real coefficients. So here's the graph of that function, and so you can see we definitely have some fractions in here, and you could figure out what your possibilities by using the factors of 16 and the factors of 3. And from your calculator, I found that 2/3 is a solution. So here is synthetic division on 2/3. And then I wrote what was left as a quartic equation, as another polynomial equation. So here's the factor x minus 2/3. And then this would be to the 4th degree. It's always 1 less than what we started with. We're missing our cubic term and we're missing our linear term. So here's how that would be written. But again, as I said in the last slide, you're always going to have a common factor that's the same as this denominator. So I factored that out, and then I distributed that to the first factor to get our 3x minus 2. So what was left here is x squared, or excuse me, x to the 4th plus 2x squared minus 8, and this thing factors as 2 quadratics. The factors of 8 that differ by 2 are 4 and 2, and then the signs are given here. So the one thing that's different in this lesson from what you're used to is we normally would stop at that point, but this quadratic right here can be reduced. This one can be reduced. It has irrational roots, okay? So that one can actually be written as x plus the square root of 2 and x minus the square root of 2. It looks like the difference of squares, but 2 is not a perfect square. But it is reducible, so we have to reduce that quadratic to these two factors. This one is irreducible because we get complex solutions only. These are not complex solutions, they are irrational solutions, so we have to reduce that quadratic. So I wanted to make sure to demonstrate one of those in your homework assignment, or in the video, so that you know what to do in your homework assignment when that occurs. See you next time.